So today we are going to continue our talk on the matter part of Unit 1, but more specifically kind of how matter can be also seen. Finishing off yesterday, this is where we left off, and that was talking about that kinetic energy and that energy of motion. At the end of class, I also discussed about how you are going to do the state of matter lab on your own. You are going to write your own procedure. You are going to do that lab at your home with your equipment. So the equipment that is listed in the materials, probably not going to be used. Okay? Don't overthink it. So, matter can be further defined beyond the solid, liquid, or gas because we have a lot of different types of substances. Now, when we talk about substances, that term is very general. And that term doesn't really tell us the whole story of what something is. Where the term pure substance, pure meaning nothing bad in it or impurities, okay? Meaning it is just that single substance, is a better term. But one of the things that you'll find, I think that becomes quite annoying, don't worry, I find it annoying too, that in science, we find ourselves saying, you might see something that is written and it's just substance. Where I like the term pure substance. So you have to sometimes read the context that it's being laid out to you in. Are they talking about a pure substance as Peterson defines it, or is their substance not a pure substance as Peterson defines it? So you have to be able to look at either or. Types of pure substances are elements and or compounds. Now elements are easy to figure out that they would be a pure substance, especially if it's the only thing that is there. And the elements themselves can't be broken down into any other substance by chemical means. And that's the important thing with that one, is that it can't be chemical means. It takes something a little bit different to break down an element. Usually nuclear fission or fusion. Fission apart, fusion together. The sun is worked by fusion and some fission. Nuclear power that we use here on Earth is nuclear fission. Ripping apart. Not all elements are found in their natural stable state. There's actually very few of them that are. They are the ones that the ancients would have realized are their earliest. Some of them, such as gold, copper, silver, were some of the first to be discovered because they can be found in their natural stable state. I mean, you could have been walking around in the desert and stub your toe on a big gold nugget. Probably something some people would be like, that'd be awesome. Yes, it would be. However, very unlikely to happen anymore. But those would have been some of the first. Some of the outlying rock structures would have some of these metals also visible and present, and therefore easier to see. Some of the last elements to be discovered are the ones that are gases. Why? You can't see them, right? Yeah, you can't see them. You're like, how do I know they're there? You have to condense them down using pressures and things such as that. Even some of the elements that were in compound form were actually in some cases thought to be in their pure form until they did some more chemical means to separate them. You won't find usually a group 1 or even a group 2 element by itself very often, because they combine with oxygen so quickly. Some of the other ones are there. Some of the elements, or at least say like aluminum, at one time was more valuable than gold. It was more valuable than gold because of the cost involved to get it by itself, to purify aluminum. Now we take aluminum from granite, right? It's cheap, it's in rolls, right? But at one time, aluminum was so expensive, it was put on the top of the Washington Monument because it was more expensive than gold. Okay? The reason why is it required electricity, and not just a little bit of electricity, it required a lot of electricity. Well, we further refined that process, and that process is much easier now. So some of those is there. Of the elements, 2 of them are liquids in their natural stable state. You know one of them as mercury. The other one is bromine. Okay? So some of these elements aren't always found as their elements. Compounds. 2 or more atoms. Now this is where science and especially chemistry gets to be confusing. Because I talk about a compound, and by definition, a particle composed of 2 or more atoms. Okay. But then you look at a molecule, by definition, a particle that results from the combination of 2 or more atoms. What's the difference? It comes down to behavior. How it behaves. A compound behaves as if it's a single thing and can be stripped apart. A lot of times, compounds are going to be known as something else. We're going to write it in here, and that is called ionic. Okay? They're 2 entities come together, and they can be ripped apart. A molecule is a particle that results from the combination of 2 or more atoms. Very similar to a compound, and by definition, molecules are compounds, but they don't behave the same way. They are usually covalent. Okay? Molecules are covalent compounds, and when they behave as if they're one single entity. Water. By definition, water is a compound. But also, water behaves as a water molecule. It behaves as if it's its own thing. It interacts with things differently as it moves through space. The hydrogen molecule is two hydrogen molecules, two hydrogen atoms. Basically, I'll just draw a circle to represent that. Little bond between them. Okay, that would be the ball and stick model for the hydrogen molecule. But it behaves as if it's its own thing. When we look at hydrogen in nature, which is hard because it's a gas and you can't see gases, right? So it's kind of a little bit of a confusion right there. Hydrogen is found as a molecule. It's found as H2. Always found in a pair. Also, I'm going to change those colors to, as another example, oxygen. We usually use red circles to represent oxygen. The oxygen molecule, the one that we breathe, the one that's 21% of the Earth's atmosphere, which is really nice, big fan of it, is always found as O2. Okay? And here becomes a thing, is when we start looking at this, you're like, but I look at my periodic table, and I always see it as just O. Yes. Go ahead and breathe all just the singular oxygen that you want. Okay? You won't be around very long. I'll take all the O2. Okay? All right. It's because of how it works. And then there's even the other molecule with oxygen, because oxygen is technically what's called an allotrope, is O3, commonly referred to as ozone. At the lower levels of the atmosphere, where we hang out mostly, ozone, bad. Don't want to breathe ozone. Your body can't work with it. At the upper atmosphere, it's a very important gas. It interacts with UV light, keeping us safe. Okay? Because what happens is that third oxygen in that oxygen molecule, there's a third one kind of attached there, gets hit with the UV light, gets broken off, and you're like, oh look, it just made oxygen. And then it gets hit with UV light again, and it basically reforms ozone. So it keeps cycling through. What happens is why when we talk about the hole in the ozone layer, and it's less talked about now than it used to be, it's the other chemicals that we aerosol, like it used to be like, you know, that whole Aquanet hairspray cans that were like back in the 70s and 80s when you needed to have that beehive all the way up there. That's when things got bad. Because it gave off compounds that found their way up into the upper atmospheres. There was other ones too, CFCs, which are chlorofluorocarbons. That were the real bad ones. They found their way up into the upper atmosphere, and they would interact with ozone and bind those oxygen up so that when UV light hit them, they wouldn't break up. And that's what created kind of the hole in the ozone. It's the compounds that we used. Once we found out, we're like, hey, probably shouldn't do that. It's the same thing with lead. We used to put lead in our piping for all of our water. And then we were like, oh, hey, that's not good. We shouldn't do that anymore. So we changed it. And sometimes in old neighborhoods, they couldn't get in and change those piping. They actually had to pump certain different use a water purification process that allowed a layer, a protective layer on those lead pipes, and then when they changed the water purification process, and sometimes it wears that layer down, and then we get lead spikes, and then you're like, oh crap, what happened? That's usually why it is. Now mixtures, they are not compounds, because mixtures can be two or more pure substances. That could be two elements, two different elements, that are in something but are not bound together. They can be separated, either by physical means, usually. It can be more than one compound coming together, and therefore can be separated. Now, a lot of times we will talk about the thing called components. Something that is within a mixture. Sometimes within a mixture, there are components that you are easy to see, and then other components that are very difficult to see. Some of that is based on the type of mixture that it is. Whether it be homogeneous, and the prefix homo being same, or heterogeneous, with the prefix hetero being different. That's kind of how you tell the difference between some of the terminologies. A lot of science terminologies have the same prefixes. It's the ending that changes. I believe a biology term is like homozygous and heterozygous. They're using the same prefix, but they're talking about different things than we are. So within a mixture, there are different components. Some heterogeneous mixtures have components that within it are also homogeneous. But yet it's a heterogeneous because there are also components that you can physically usually see the difference between them. That's your main different type. That's where the separation usually entails. So we'll look at each of the mixtures a little closely. As I have on the picture here, Kool-Aid. When you mix it with water, it becomes a solution, but not an answer. Be careful with that, okay? Meaning it's the same composition throughout. We can't visually see the difference. And a lot of times our homogeneous mixtures are going to be solutions. Now, when we go into the lab, you have already used solutions. You grabbed the bottle that said base, or the bottle that said acid, even though the acid was actually bleach. Therefore, it's actually a base. But it's the sodium hypochlorite that gets rid of the phenolphthalein that makes it have a acid quality to it. But it's just that compound interacts with it in a way. So those are two solutions, because you can't see the difference between them. Now, as we go through the class, we will add in the lab more and more solutions, but not answers. Okay? When I am at home and I grab milk out of the fridge, the first thing I do is homogenize it. Meaning, I'm making it the same throughout. How do I do that? Give it a little shake. Okay? I mean, it's not like, Polaroid picture or, shaking it off like T-Swift. Okay? It's just a little shake to kind of homogenize it. I do the same thing with my OJ. Because I prefer OJ with a little bit of pulp in it. Okay? Now, if I let that OJ sit in my fridge for even just overnight, what happens? Splits. Therefore, it becomes a heterogeneous mixture. You can visually see the difference. Now, if you go in and grab your milk out of your fridge and it's a heterogeneous mixture, don't drink it. Okay? Don't drink it. I shake it just out of pure habit. Because when I was in college, we had a lab, well actually it was a class, that in lab, you wanted to make sure that you got as good a grade as you could in the lab, because then you didn't have to do the lab over again. So you always shook your solutions or swirled your solutions before you poured. So it became a habit. I still do it. The only one I don't do, I find myself kind of going for it though, is the water out of the Brita pitcher. The Brita pitchers? Yeah, sometimes I'll grab it and I'll kind of just do a little shake on there, okay? But not enough where the whole top goes flying off. Okay, learn my lesson the hard way. But that's what you do. And a lot of times we like to use like trail mix as the example for the heterogeneous mixture. Why? Because we can see all the wonderful things inside there. And really what it comes down to is people always take out the cashews first. Right? Now, if you're a good host, you buy an extra bag of cashews and dump it inside there so that you have more cashews for your people. Or you're a bad host and you buy trail mix that does not have any cashews and buy a bag of cashews for yourself. Okay? However, that's where you see all the different components. Now, Kool-Aid, before you put it in water, can be considered a heterogeneous mixture. But there's components within Kool-Aid that are also a homogeneous mixture but then you can have mixtures within inside mixtures. Okay? And that's where things you're like, okay, what is what and what am I looking at? And that becomes the problem sometimes. You have this wonderful flow chart. So this flow chart has a lot of good information. It kind of has that yes, no, which one is it? And so you have is it uniform throughout? Yes or no? If yes, you go there. Is it homogeneous? Does it have a variable composition? Yes, no. If no, pure substance. Can it be separated in simpler substances? Yes, no. If yes, it is a compound.